Hello everyone, let's continue with the definitions for propagated noise low and the propagated noise high. For that purpose, we are going to take this inverter as our channel connected component and we'll try to characterize this component in terms of noise. So let's try to do that. So now take a note of all the inputs or all the nodes over here. You have the aggressor in node, which is the input for the complete aggressor set of inverters. You have the victim in node, which is the you have victim in input, which is the input for all the victim inverters present over here. You have the aggressor out, you have the victim out, you have the aggressor line out, you have the victim line out. Let's try to look into the waveforms of each and every one of them one by one. So for example, we have this one. Let's say your aggressor in was switching from logic 1 to logic 0, and then again eventually from logic 0 to logic 1, and it switches from logic 1 to logic 0 at 0.6 time nano or 0.6 nanosecond, and finally it moves from logic 0 to logic 1 at around 3.1 nanosecond. And your victim line is kept static at logic 1. So the blue is your victim line, the red one is your aggressor line. Now if you look into the output, for example, if you look into the output of aggressor out and the victim out, this is how it will look like. So these were the inputs and these are the outputs. Your outputs will look something like this. Your output will be switching from logic 0 to logic 1 for the aggressor input, which was switching from logic 1 to logic 0, and it will be stable at logic 1 for some time, and finally at about after 3.1 nanosecond, because your input switched from logic 1 to logic 0 to logic 1 at about 3.1 nanosecond, your output will switch from logic 1 to logic 0 after a certain amount of delay. Now if you look into the victim out, because of the huge capacitance that we had huge mutual coupling capacitance that we had placed between the aggressor out, which is this one, and the victim out line, you see a bump over here. The output, which was supposed to be at logic 0 constant, because your victim input was at logic 1, your output is supposed to be logic 0, but because of this particular sharp transition and because of the huge mutual coupling capacitance between your aggressor and the victim, you see a bump, you see a current flow from this point during this period of time whenever your aggressor is charging. Again, you see a bump at the negative side due to the discharging of your aggressor line. So this is the bump characteristics. So this is how your bump will look like. Now the important point to note over here is, how does this particular bump propagates, or does this bumps propagate to the output of the victim inverter? So let's see. So for example, this is the final output. The aggressor line out looks something like this, same as the input, and this is how your input was switching, and the aggressor and the victim line output, which was supposed to be at logic 1, because of the two inverters which is present in the path, it faces a slight bump at the input side whenever your aggressor line is switching from logic 1 to logic 0. This input bump that you see over here is nothing but an inverted version of this particular bump that you see. Okay, and there is the bump that you see at this point of time, it doesn't get captured at the output side, and there are reasons why we see it. So I'll explain the reasons in a moment from now. If you look into this particular channel connected component, and if you look into this particular waveforms, these are the inputs to your waveform. So this bump and this bump are the inputs to your channel connected component, which is an inverter, and this is the output to your channel connected component. Now if you observe over here, this particular bump was basically inverted at the output, but this particular bump was fairly filtered by the output, or fairly filtered by the inverter over here. The STA tool, this particular things needs to be captured inside a inside the noise library in such a fashion that the STA tool understands which noise bump propagates and which noise bump doesn't. So for that, we need something called as propagated noise low and propagated noise high, and that table is referred to as, or that curve is referred to as, noise immunity curve. So a noise immunity curve is nothing but a set of values which is being specified as a table that defines which of this particular input curves, which of this particular input bumps goes through the inverter and which doesn't. For example, if this kind of information, this sizes of information is present in the table, the STA tool will take that information, and if it sees a bump which is of this height, it will safely ignore it. And that's what is called as a noise immunity curve, which is present in form of propagated noise low and propagated noise high. So let's look into how does that table look like. So for example, if you look into the initial diagram that we had used, or the setup that we have used, so what we'll do is we'll take the CCC outside and we'll try to characterize that particular cell for your noise immunity curve. So you have an input pulse. We're eventually going to get a triangular waveform out of this pulse source. You have an output capacitance. Let's say we'll start with a value of 10 femtofarad, and we have the VDD supply. After you have this setup ready, it's just a matter of plotting converting the waveform. So let's try to do that. You have this victim in as the input node, you have the VIC out as the output node. So this is how your waveform will look like. So for example, in the first case, we try to draw this triangular waveform as an input and we see what is the output. So in this case, your triangular waveform starts from 1.8, it goes till 1. So basically there is a dip of 0.8 volts, and then it goes back to 1.8. So this is a triangular waveform. This is the input noise width, and this is the input noise height, and this is the noise area. So these are the terms that we are going to use to define the noise tables or define the noise immunity curve. So I'll get back to that in a moment from now. So if this is the input, this is the output for 10 femtofarad. So if you look into this particular bump, it's very small for this particular triangle. So this information gets stored in the library in certain format, which says that if you receive a bump which is of this width and this height, the output bump should look something like this for an inverter. So similarly, if I change the bump, if I change the triangle height to let's say again by 0.1, 0.2 volts, so 1.8 to 0.8, there is a 1 volt noise height. The width is about, let's say it's about 50 from 50 to 450 picosecond, so it's about 400 picosecond. If you receive a noise bump, so this information is being stored in the table and is being interpreted by the STA tool in such a format that if you receive an input of, if you receive a noise input of width 400 picosecond and of a height of let's say 1 volt, this is the bump at the output that we will receive. Similarly, if you try to increase the height of your input noise width, it looks something like this. The size of the bump goes on increasing because of the strong mutual coupling capacitance that we have, and because of the strong noise input signal. Okay, and the strength of the noise input signal decided upon the width and the height. So basically it depends on the area of this particular curve. So next, if you increase it even further, if you see, you can see a huge noise bump which is present at the output of the inverter. This is the propagated noise high value. Okay, let's try to squeeze in this particular triangular waveform. So it's again dependent. It's dependent not only on the noise height, but it is also dependent on the noise width. So let's try to squeeze in the width for some time. So if you see, if I have squeezed the width by about 50 to from 450, I brought it to 350. So I have squeezed the width by 100 picosecond, and this is how your noise bump will look like. Again, I will squeeze the noise bump. I'll squeeze the width by some more 100 picosecond, and this is how noise bump will look like. So if you look into the triangular waveform over here, even though your noise height is quite high, since your width is quite low, you don't see a huge bump compared to what we saw initially. Again, if you try to squeeze your noise input noise width even lower, you practically don't even see a bump. Okay, so that's the concept. So if you see a higher noise width but a lower noise, if you see a higher noise height but a lower noise width, so this might eventually get filtered out by the inverter, because inverter acts as a low pass filter. All the high frequency signals will get filtered out. Okay, so this is basically your noise immunity curve. All this information are stored in form of table, and this is how the table will look like. So this is propagated noise high. This is a lookup table. I've just given a name called as lookup table. You might find different names over here, and there will be 4 indexes and one particular value matrix over here. So you have the index 1 as the input noise height, index 2 as the input noise width, total output net capacitance. In this case, we did everything for a 10 femtofarad capacitance, so we'll have 10 femtofarad capacitance, and index 4 will be time units at which you see the pump, and voltage, and these are the voltage value for this particular time. So let's take an example of what we did just now. So for example, in this particular case, your width is about 50 minus 450, which is 400 picosecond. Okay, so that is what is being mentioned over here. Your input height, your noise input height is 1.6 volts. So let's calculate that. So it's 1.8 minus 0.2, it's 1.6 volts. Okay, so we have the value over here. Your output capacitance is 10 femtofarad. So we have characterized this thing for 10 femtofarad. Your index 4, which is the time units, will look something like this. So if you see over here, it's from this point we increase the bump height, we increase the input noise height. So it's 50, 100, 150, 200, 250, 300, 350, 400 and 450. So we characterize this, or we create this noise bump for this kind of value. So let's say we'll start with 150, because your output actually starts from 150. Your output starts to increase from 150. So let's start with 150. And we'll go on increasing 50 picosecond every time. So it's 150, 200, 250 and so on. And for each value of the time, you will see we'll try to plot the bump over here. So for each value of the time, for 150 you will see this value, for 200 you will see a value of 0.1 volts, for 250 you will see a value roughly about it's about less than 0.4, about 0.37 or something. For 300 you will see a value of 0.67 volts and so on. So these are the values, these are the entire thing that will get get plotted over here, or that will get filled in the value sections over here. Now if an STA tool refers to this particular table, it knows that if it receives an input bump which is of height of 1.6 volts, a width of 400 picosecond roughly, and an output capacitance of 10 femtofarad, this is the noise bump. Now whether do we need to filter this particular noise bump or not, that depends completely, or that is entirely dependent upon the designer. So the designer has to decide whether this noise bump is acceptable or not. Okay, so that's what propagated noise high means. So, and why it is called propagated noise? It's because we are propagating the high level of the noise. If we had propagated the low level of the noise, it would have called propagated noise low. So that is the table of the propagated noise high, and that is the syntax of the propagated noise high, and this is called as the noise immunity curve. This basically is called as a noise immunity curve for a cell. So what we'll do is we'll stop at this point, and from the next video we'll start with the next syntax, or the next information, or the next pin based CCS noise model, which is stage type. So let's start with the stage type from the next video. Thank you.